my name is Takumi KODAMA from Multimedia Laboratory. Today I will present my research project. The title of which is Full-Body Spatial Vibrotactile Brain-Computer Interface Paradigm. So at first, let's begin with a brief introduction about BCI. BCI stands for the Brain-Computer Interface. This interface can exploit user intention only using human brain waves. So please look at this figure. These three diagrams is showing the main function of the brain-computer interface. The BCI receives the human brain waves in the signal processing section, and the brain waves are pre-processed before converting feature vectors in the feature extraction section. And finally, those feature vectors are classified by the machine learning algorithm in the classification section. If successfully understand this classification section, what the BCI user is thinking about. The BCI interface can send any command to the applications. The main purpose of this application is to enhance the human function or human movements, like human robot or wheelchair or language system. Then these applications will give feedback to the users. This closed loop is the BCI's main functions. So the technology is mainly developed to help to assist the ALS, which stands for the amyotrophic lateral sclerosis patients. They are having difficulty to move their muscle by themselves. So they are actually very difficult to say something and to move to tell their intentions by gestures. So BCI, which only requires the brainwaves for the two inputs, there could be a communicating tool between those patients and their care workers. So my research approach in the BCI study is a tactile P300-based BCI paradigm. The main purpose of this P300-based BCI paradigm is to find these P300 brainwave responses in response to the external stimuli, like a visual or auditory stimuli. But in this project, we have applied the tactile, the touch stimulus, vibration stimulus to this BCI paradigm, and then to evoke this brainwave responses. We gave the random vibration stimulation to the BCI users during the experiment. The BCI user selects one of those commands. Then, if successfully, he can respond one of those commands. The P300 responses are occurred in his brainwaves, and these brainwaves are converted to the feature vectors, and machine learning predict this user's intentions. So there are some previous researches so far. These are actually developed by our laboratory. The one example is a chest tactile BCI, which attaches the small tactile exciters on the chest areas. Another example is a tactile and auditory BCI, which attaches the small exciters on the head and facial areas. So these interfaces are well investigated. However, these are having some problems. The one problem is the discrimination of each stimulus pattern. Since the chest and facial area is a very limited area, so the stimulus pattern, the stimulus pattern is attached to the very closed area. So sometimes the BCI users are difficult to distinguish those stimulus patterns. Another problem is the application for the ALS patients. Sometimes those care workers are very hesitant to touch facial area, or those patients are sometimes does not have touch senses at all on the certain areas of the body. So to solve these problems, in this project we try to propose a new tactile, touch-based BCI paradigm, especially communicating, applying for the ALS patients. And by creating the new BCI paradigm, we will confirm the effectiveness of the modality, thereby improving the stimulus pattern classification accuracy, which is our most important criteria in the BCI study, which is actually correct rate, command correct rate of the BCI users in the BCI studies. So this is our approaches. The full body tactile PC hand-based BCI, we call it as a FBBCI. We apply the 6 vibrotactile stimulus patterns to users' whole back and limbs. We placed these big exciters on the Japanese style mattress to create 6 vibrotactile stimulus patterns to especially to stimulate to the left. Pattern number 1 is for left hand, and pattern number 2 is right hand. The 3 and 4 is shoulders and waist respectively, and the 5 and 6 are both legs. And then another benefit of this this interface is the user can join this experiment with their body laying down. So since most of the ALS patients are bedridden situations, so they are very easy to join, easy to use this interface. So to validate the FBBCI paradigm, we conducted 4 experiments. The first experiment is a psychophysical experiment. This is considered as a pre-experiment before the EEG experiment. The second experiment is the EEG experiment, which is supposed to be the most common, usual, the experiment. We conducted the 1 and 2 experiments simultaneously. Then after that, we tried to improve the classification accuracy, the correct rate of the BCIs, by using the SDM classifier and SWLDA classifiers. This experiment was conducted in the offline situation, which means just to calculate the classification accuracy. We did not employ any BCI users. Then finally, we also tried to apply the CNN, convolutional neural network algorithms to the BCI studies. At first, I will introduce about the psychophysical experiment. The main objective of psychophysical experiment is to evaluate the FBCI stimulus pattern feasibility. So we did not attach the EEG caps or EEG electrodes on the BCI user's scalp. We just asked the kids to button press if he feels the target stimulus which presented in the display. So the 10 users participated to the psychophysical experiment, and the stimulus frequency of the exciters was set at the 40 Hz. The vibration stimulus length was set at 100 milliseconds, and interstimulus interval, which is a duration between each vibrotactile stimulus, was set at 400 to 430 milliseconds. And one experiment was conducted to each user. Because this is actually pre-experiment. This confusion matrix is the result of the psychophysical experiment. The vertical is showing the intended target which we designate to concentrate to the BCI users. And the horizontal is showing the actual subject response, button press response. Each number is associated to the FBBCI stimulus pattern from 1 to 6, and in each correct cells, the correct rate exceeded 95% in every stimulus pattern, so we could confirm the validity of each stimulus patterns from the experiment. The second, we conducted EEG online experiment. Like I said, this would be considered as the most common usual BCI experiment. We attached EEG electrodes on the user's scalp, and his brainwaves are converted in the EEG amplifier to input to the computers, and then BCI classified his EEG signals. The objective of this experiment was to reveal the FBBCI classification accuracy, the correct rate of each users. Since this experiment was conducted with the psychophysical experiment, above follow is completely same as the psychophysical experiment. But we conducted 1 experiment for the classifier training and 5 experiments for the for the evaluate for calculate classification accuracy. The important things here is that each the subject the classifier model is generated to each subject. For instance, the subject number 1, the ERP signals are classified with the subject number 1's classifier model, and also for the instance, the subject number 1's ERP signals are classified with the subject number 1's subject number 7's the classifier models. The EEG sampling rate was set at 512. Electrode channels are attached to the central areas, and SWLDA, which is a linear discriminant analysis with the variable selection using the stepwise regression, was applied as a classification algorithm. So this is the ERP intervals, which is a duration after the vibrotactile stimulus are given to the users. The length is 800 milliseconds. Just 100 milliseconds is given. Just 100 milliseconds. The section is given to the vibrotactile stimulus to each user. So in each electrode channel, we could confirm the strong P300 responses. Only when the target stimulus is given to each user. This is actually the grand mean ERP intervals, which means the all average, the mean result of the all participated users. So this blue dotted line is the non-target, the ERP intervals, the EEG signals when the non-target stimulus is given to the users. The gray shaded area in each graph is showing the significant differences between the ERP signals for the target stimulus and non-target stimulus. Then these ERP intervals are converted to the feature vectors, and machine learning classifier classifies those ERP signals, and the result was this classification accuracy result. Like you see, the average of the 10 participated user result was 53.67%. This is relatively lower than the other visual or auditory modality. So we needed to improve the classification accuracy with the offline experiment. In the 3 and 4 experiment, we did not employ any users. We just calculate on the personal computers to improve the classification accuracies. The third experiment is main objective of third experiment is to improve the classification accuracies with new method or changing some settings of the BCIs. As I showed you at the first of this presentation, that these are main functions of the brain-computer interface. We try to modify some parameters in the signal processing sections by changing signal decimation factor of the downsampling from 1, 4, and 16, and changing ERP average settings from 1, 4, and 10. And finally, after those signals are converted to feature vectors, in the classification section, we try to apply the new classifiers, which are SVM and nonlinear SVMs. SWLDA is the same method as the online experiment, but we also calculated with this classifier in offline experiment. So this is the result of the accuracy refinement experiment, offline experiment with the SWLDA classifier. The best result was 57.85%, which is better than the online SWLDA classification accuracy result. Each bar is showing the signal decimation factor difference, the 1, 4, 16, and each the horizontal axis is showing the non-averaging difference, non-averaging and 5 averagings and 10 averagings. The y-axis is showing the classification accuracy. The best result was when the non-epoch averaging and 4 signal decimations. So this is the result of using a linear SVM classification accuracy, the kernel of which is described as this equation. The best result was 58.8%, when the destination factor was 16 and 10 ERP averaging. This is the result of non-linear SVM classification accuracy. This is actually the best result of the experimental 3, which is at 59.83%, with the for-signal decimation and non-epoch average. So at the final experiment, we try to improve the convolution neural networks to the BCI ERP classification of the FBBCI. The main objective is the more improvement of classification accuracies by using the new method. And this is new the purpose of this experiment. Actually, to achieve non-personal training ERP classifications. So this means that before a previous experiment, that we try each subject need to generate the classifier models. Like as user number 1 need to create classifier model for the subject user number 1. However, in this experiment, we try to apply the non-personal training experiment. For instance, when the ERP classification of the user 1 is evaluated, the classifier model, we try to use the classifier model trained by user number 2 to 10. In another case, when the user number 10's ERPs are classified, we try to apply the classifier model which trained by the user number 1 to 10. And also the feature vectors, we have applied one-dimensional feature vectors, but in this experiment we try to transform the one-dimensional vector to the two-dimensional squared matrix. So I will introduce about it. This is the method of transforming feature vectors to the input volumes. This is actually each column, previously the ERP intervals, the length of ERP intervals was the 1 to the 410 length. And at first we try to cut the beginning of the first 10 elements to create 20 by 20 squared matrix. Then each elements are deployed from the top left to the 1 to 20, and on the second column 21 to 40, and finally on the final column 381 to 400. And each squared matrix is concatenated. This is actually generated by one channel, and then we concatenate the squared matrix we try to concatenate all channels of the squared matrix to one squared matrix by a 3 by 3 grid. And we also use the mean ERP signals of all the electrode channels on the center of the grid. So this is an overview of the CNN architecture that we have used in the FBBCI. That we apply the two convolution layer as the pooling layer, which imitated LeNet. And the 60 by 60 is the input volume squared matrix. Then this layer is convoluted in each layer. At the final layer, the number of the filters are 50, and the 12 by 12 the filters are input to the one multi-layer perceptor with the one hidden layers. So this is the result classification accuracy result of the CNN application. We try to apply the two settings. The one setting is a non-epoch averaging, and the another setting another settings is a simple moving average. We have to average the ERP signals with the moving average. The result was the 79.66% in the result of the non-averaging result, and 100% in the results by averaging the 10 participated users. So let me summarize this presentation. The validity, we confirmed the validity of the FPVCR paradigm by 4 experiments. On the first experiment, we confirmed the stimulus pattern, the feasibility. On the second experiment, we tried to conduct experiment in the online situations. On the third and fourth experiment, we tried to apply new classification method and new on the offline environment. In the future study, we need to improve the QOL to help the ALS patients. By this modality, we need to conduct experiments with the practical conditions. Since we haven't tried, we haven't applied this modality to the ALS patients. And also we need to implement the third and fourth high classification accuracy result to the online experiment, since these experiments are conducted in the still offline situations. And finally, I hope the series of the experiments results will contribute to the development of the BCI study and also the tactile P300-based BCI paradigms. So these are the publications which we published already. This is the journal article, and this is a book chapter as a co-authored. These are conference papers list. Some of them are received some awards, and this is also the conference papers, and this is also the co-authored conference papers. Thanks for the listening. Would you have any question or comments?
はい、それではご質問